Right. Yeah. Thanks for the very nice introduction, and it's really my pleasure to be here today. So for people who know me, know that I have given a lot of talks in the past 1 or 2 years on various aspects of agents, but those are mostly like technical talks. And then when presented with this opportunity with Ivado at this workshop, and at this very special timing, right? We are coming to the end of 2025, and 2025 was known to be the year of agents. So I feel like it's a good opportunity to to retrospect a little bit about like where we really are in terms of developing these agents. Are we there yet? So that prompted me to write a new blog post called Computer Use Modern Moravec's Paradoxe. You can find it online there. And because of this is like a new thing I just wrote, so I literally just like finished the slides last night. So bear with me if there's like a bit of a hiccup here and there. But let's get started. All right, we'll start with a bit of history. Let's go back to the year 1966. At the time, the field of AI has been making tremendous progress on what's considered the crown jewel of intelligence at the time, symbolic reasoning. Like we have like a great theorem-proving algorithms that even proved some of these mathematical theorems like in a way more elegant than the original version in the textbook. And we have this early checkers program that's trained with some early version of reinforcement learning. And we have ELIZA that gives the world a glimpse of these chatbots that converse like humans. So the field was very optimistic, right? We were making progress on these like hardest problems, at least considered hardest at the time. So then people started to tackle something that seems easy, at least to humans, seems effortless to humans, which is visual perception. So the summer vision project was started in Minsky's lab at MIT. That was like one of the first computer vision projects. A group of undergraduate students were recruited to solve this seemingly easy problem, like develop an algorithm to describe the objects in an image. Well, that summer project turns into a multi-year grind and eventually a small fiasco, according to some other computer vision pioneers. And image captioning didn't mature until like the 2010s, like 5 decades later. So this stark contrast between like the difference in the difficulty between these like tasks that seems hard for humans but that turns out to be not so hard for machines, and then these tasks that are hard seems very trivial for humans but very hard for machines is later known as the Moravec's paradoxe. So many AI researchers, including Minsky himself, realized this problem at around the 1970s and 80s, but Hans Moravec from CMU summarized this very well. Right? It turns out it's easy to make computers like do adult-level performance on like intelligence tests, like these symbolic tasks, but very difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. Right? In retrospect, this paradox is counterintuitive, but not too surprising, but understandable. Right? So if we consider evolution, like true symbolic thoughts only evolved mainly in our like Homo genus, which like maybe at the most like 2 million years ago. Well, perception and mobility are highly conserved through evolution, containing many mechanisms that can date back like hundreds of millions of years. This doesn't necessarily make them more intelligent than symbolic thinking, but it does give like natural selection more time to optimize them And we end up with many sophisticated yet bespoke mechanisms for perception and mobility. For example, we have like very specialized areas in the brain for face recognition, right? Even like monkeys have like specialized mechanisms for like fruit detectors, or like we have like a disproportionately large area in the neocortex for our hands, right? And that's still something that like it's very hard to tackle in robotics today, like these dexterous hands. So another reason here is that the perception and the mobility mostly happen subconsciously, right? So that makes it even harder to kind of introspect and to reverse engineer the underlying biomedical mechanisms. So interestingly, in 2025, a modern version of Moravec's paradoxe seems to be unfolding. And that has something to do with computer use agents. So let's see a demo here. This is ChatGPT agent that was just released, I think, 1 or 2 months ago. And this is the task on the left-hand side. So the ChatGPT agent will spin up a virtual browser in the cloud and then tries to do this task. You can see on one hand, it does look like a human that is using a computer, okay? It looks at what's on the screen, think about what to do at this state based on the task, and then just do that. And if it run into errors, then it will introspect and then try to recover from that. So that's great. But on the other hand, it is also very slow and brittle. For this simple task that the human probably takes like 1 minute, so ChatGPT agent took, I think, about 4 minutes at it and eventually got stuck. So it didn't solve it. But if we compare what ChatGPT agent is doing and what humans would do at the same task, we find that humans would be much faster and robust. We don't need to do as much reasoning on the fly or like this thinking out loud as ChatGPT agent is doing. Like a lot of these simple things have become kind of like a muscle memory for us because we have done or seen similar forms on other websites before. And we to be much better at like recovering from errors, like or judging whether we have achieved the task or whether we are on the right track. So it seems that there are a lot of these subtle underlying cognitive competencies that's going on that makes our humans computer use so easy, but that seems to be still missing in the current computer use agents. Right? So that's what we're seeing as a modern version of the Moravec's paradoxe. On the one hand, we once again are making jaw-dropping progress on symbolic reasoning, and this time on much harder problems like mathematics, like coding. Right? We have more or less outperformed the best humans on these problems, at least in some limited settings like Olympics competitions. And also, vibe coding has gotten so good that it's become the mainstream. If you haven't tried like AI-assisted coding, please go try that. That's just amazing. But on the other hand, in just like 2 years, I think computer use agents have indeed become like one of the hottest areas, one of the most contested battlegrounds for these AI powerhouses. Like OpenAI has like operator that later evolved into ChatGPT agents. Anthropic has their like computer use agent as well. Google has like Project Mariner. Microsoft has a bunch of offerings, and then Amazon has their Nova agents, and so on and so forth. So it's not like we are not trying. Everyone is trying very hard at this problem. But on the other hand, ironically, current computer use agents still struggle quite a bit towards the end of 2025. Even just on these like simple academic benchmarks like OSWorld, like WebArena, WebArena, or Online Minds Web, there's just mostly at like a 50 to 60% range, which is very far away from like the 99.9 that Russ mentioned that we need. And remember, in these academic benchmarks, these are mostly like simple tasks with like a task horizon of like 10 to 20 steps. And they are far more, like a lot of the tasks that humans want this agent to do are much more sophisticated than that. Right? So that's the modern version of Moravec's paradoxe. We're great at symbolic reasoning, but we struggle with computer use. Because like for computer use, there are really a lot of like underlying cognitive competencies that are required to make that work. That's like planning, grounding, word modeling, memory, and social norms. Like it's not like these are fundamentally harder than like math, reasoning, or coding, but they are cohesively a different set of challenges that the community has not yet paid enough attention and investment into them. So let's see why computer use is so hard for current AI. There are a couple of reasons. First, computer use, even though on the surface it seems easy, it's just like a clicking and typing, but there's a lot going on underneath. Right? We mentioned some of this earlier. I think an interesting analogy here is think about like next token prediction for language model training. Right? It seems that it's this simple task, okay, just predict the next token. But in order to do that well at scale broadly, the model has to internalize the original, like the latent data generation process in order to do that. And that's the same thing for computer use. You need to have all these other like cognitive competencies in order to make it effortless to do these clicks and typing. Another challenge here is contextual understanding. Right? We rely on a lot of context when making these decisions in the digital world. Right? For example, when we are like ordering groceries, right? We know our brands, so these are like our default go-tos. But we also know, okay, maybe this month like my budget is running low, so I should like choose those generics instead of like my go-to brands. But how do computer knows that? How do the computer use agents know that? And that's related to the question that was just asked earlier. Right? If you ask the user to write everything down to specify everything, that's so tedious, and that defeats the purpose of these agents. Another challenge here, so those challenges are more on like the agent part, but another challenge here is more on the environment part. That is, these digital environments are highly idiosyncratic. Right? Every website, every app is like an idiosyncratic, ever-changing micro world. Right? So, maybe a good analogy here is you think about like like a database, right? Each database has a schema. The names, the schema names, right? They are entirely up to like the database administrator. I can call this like column A, column B. I can also call them in a more semantically meaningful way. That's just up to them. And similarly, on a website, what exactly a GUI element is called, or like the specific transition dynamics on the website, that's just up to the website developer and the business owners, right? So they are highly idiosyncratic, and they are highly dynamic. And then from like information theoretic perspective, I think it's implausible, if not impossible, to say that we will have like a monolithic model, like a very powerful LLM, to just master everything in the digital world. Because there is like an infinite amount of information. If you have a model with just a limited capacity, no matter how high that is, it's just impossible for that one model to capture everything. So I'm a big fan of, and I strongly believe we need modular systems with components that are adaptive so that they can capture these idiosyncrasies. Finally, it's about tacit knowledge. Right? Humans accumulate a wealth of implicit know-hows about how to do things on a computer. Like maybe it's like the different processes for reimbursing different things, or maybe it's like different approvals needed to make different purchases, and so on and so forth. A lot of those are never like formally documented. And so an extreme example of this is what I call the AWS console problem. Right? For anyone who has used the AWS console, it's like notoriously hard. Right? There are like hundreds of tools on there, and that can be orchestrated into thousands of different workflows. So it's a ton of tacit knowledge. It's so complex such that even human professionals typically take a month of dedicated training to get a certificate. So if you just put an LLM-based agent at it, it's just like an intern right out of college. So it can do something, but it can never do anything sufficiently well and robustly. So it has to do like extended continued training on the job in order to really become an expert, which is currently lacking in agents.
Can I ask you a question? So, but why do the existing data sets, I feel they are too simplistic and does not have some of these problems that you mentioned? Because it's all fully specified. If you take web instruction, right, it's fully specified. Or WebArena instruction is fully specified. Even in those cases, why do you think the agents are having problems?
Yeah, that's a great question. So first of all, like my standpoint is mainly from like how to really make agents work in real world, and hence this like these challenges. For these academic benchmarks, I think there's a combination of reasons. First of all, I think the latest models are pretty good at them. In fact, we are just testing Claude 4.5 on online Minds Web right now. I think it's getting to like 80% range. So pretty decent, but still not ready for like practical deployment. On the other hand, there's always this, if you actually look at the tasks on any of these benchmarks, including the ones from my group, there are always these like peculiar examples in there that's just like so out of distribution that makes it hard for these agents. And then there are always like a certain amount of annotation errors. Okay, but before we get to a more technical discussion, I want to also share a bit of like why computer use is so exciting. Because it's so challenging, but if it's not like a super important problem, then maybe we don't need to spend so much time at it. We just forget about it. In fact, I think computer use is maybe one of the most exciting research frontiers right now. So we know the success of AI, the LLM paradigm today, the main driver is the data. Right. It's more important like any specific architecture, optimization algorithm, or hardware. Right. The data is always like the source of intelligence. But we also know that we have exhausted more or less like the high quality part of the data on the internet. So everyone is thinking about where's the next internet scale data or learning opportunity. Because like, the current models, especially agents, they are not there yet, right? They are not this like very capable agents that can sustain long horizon goal-directed behavior. And I think computer use may be the most promising setting for that. So generally, we are moving away from chatbots to these agents that can sustain goal-directed behavior. And the digital world is extremely broad and deep. Then billions of humans are performing these diverse, complex, goal-directed activities there every day. So that creates like unlimited learning opportunities if we can unlock that. On the other hand, a major difference between chatbots and these agents is that, so LLMs, they are mostly trained on this the data that's already on the internet, right? Those data is mostly artifacts from like human cognitive processes, right? So maybe the LLM is trained on a well-polished paper, so you can predict the next tokens. But what the agents need is to directly learn the cognitive processes that produce that paper, right? How do you come up with hypotheses? How do you test your hypothesis? How do you formulate your experiments? How do you write the paper back and forth? So agents need to learn these messy cognitive processes, not just like these final artifacts. And computer user agents is about that. So it's a natural vehicle for that type of learning. And another strong contender here is embodied agents or robotics. Like recently, it has seen like a ton of investment. I think both are very exciting, and both can potentially provide like, the next internet-scale learning opportunity. But I think the timeline-wise, these digital agents, they just face so much less barriers. Like this, you don't need to deal with like this hardware, the wear and tear, this like very low-level control problems. So in terms of the timeline, I think digital agents will probably be a much more attainable milestone than physical robots. And finally, obviously, it has like enormous economic value. If we can develop a truly capable digital AI worker, then that would be a game changer for virtually every industry. Right, so this is a very exciting area. Okay, next I will very briefly talk about a few of our recent technical work. And I chose this work because they are, I think, they are representative of some of the areas that I think are very important for the next stage of agent development, but are currently not that many people are looking at them. So I think they deserve more attention. And so hopefully this will provide some food for thought. And much of this work here is done with my colleague Huan Sang here in the audience. I will first talk about evaluation and the reward modeling using our work called Mind-to-Web 2. And then we'll talk about word modeling and model-based planning using WebDreamer. And then non-parametric continued learning with Skill Weaver. So Mind-to-Web 2, where we evaluate agentic search with agent as a judge, led by students Bo Yu, Zhang Ming, and Yu Ting. It's in collaboration with Amazon AGI Lab. So we're seeing a very quick evolution of how search is done, from the traditional web search on Google to agentic search. Right? We have evolved from Google to ChatGPT to like Operator, these kind of web agents to deep research agents, and now hybrid agents like ChatGPT agents. What's going on here is that the search is evolving quickly from a user-driven activity, where users have to decompose their search intent to do the search, to synthesize the information and iterate that process, to a largely AI-driven process, where AI is doing most of the low-level activities and in a much faster way, and then humans just need to be in the driver's seat and do the oversight and make critical decisions. On the other hand, so that is great. I think that's very useful. I use agentic search many times every single day. That has really improved my efficiency. But on the other hand, from an academic perspective, it also gave us an evaluation crisis, right? So here is results from a deep research system where I asked it to survey all these deep research systems, and it gives us these long reports. So there are many challenges in terms of how to automatically evaluating these results, right? These tasks are extremely long horizon. They can easily take hundreds of steps to arrive at this answer. And these answers are can vary over time. It's not just like a fixed thing, so you can do string-based like comparison. And the answers are complex, multifaceted. You need to evaluate different facets. And you also need to evaluate hallucination and attribution. Like, how do you know? Like, here, the system claims that DeepSeek R1 is a deep research system and cites some source to back it up, but it's actually not. So how do you detect that? That's why we take an agent as a judge approach to tackle this evaluation crisis head-on. Essentially, when you have more intelligence, more autonomy in your agent system, you should also inject more intelligence and autonomy into your evaluation system to keep up with the pace. Right? In MindWeb 2, it features these realistic long horizon tasks like this. Okay, I want to find all this like furniture on IKEA, and so the answers, as you can imagine, will vary over time. The different users or you search at different times, you will get different results. And most of the tasks in MindWeb 2 like span multiple websites. Then these agentic search systems will return these complex answers, like hundreds of thousands of tokens with citations like this. So you can actually go to the cited web page to see whether that's true or not. Then it covers diverse domains. And then the most important thing is the agent as a judge evaluation methodology. And we will talk more about this right now. Right. So for each task, we know a priori what that task is looking for. So we can try to write down a rubric tree to detail how the evaluation should be done. This rubric tree, you can imagine, like maybe this is the root node, then maybe each of the child node here, because this task is looking for a bed frame, a desk, a chair, then maybe each node here corresponds to each of the items here. So maybe these nodes correspond to like the bed frame. And then you can further decompose the evaluation of the bed frame, like whether it's indeed white, because we're looking for like a white bed frame, I think, and whether it's indeed from IKEA and so on and so forth. And then you can aggregate these results into the internal nodes and then further propagate. So essentially, we decompose the evaluation of each task into such a rubric tree. And at the leaf node level, each leaf node here is like an LLM call. Right? You use an LLM to extract some information from the answer, and based on the preset criteria to make a binary judgment whether that's true or not. Then you aggregate the results following the tree structure. So this is an agent, judge agent, because this tree essentially defines an agentic workflow to like how to evaluate this task. And each task has its own judge agent and rubric tree. So it's different for each task, because each task is looking for different things. More concretely, let's say you have these nodes in the tree that's judged for the wardrobe, right? And it can be further decomposed, like whether this is from IKEA, whether the price is accurate, and so on and so forth. And then you can go to the cited URL to judge that automatically using LLM. You also have like some more global criteria, like whether the aggregated price of all these 5 items is indeed within my budget. Okay. And here's an overview of the benchmark. These tasks are very complex. You can easily, like for humans, here, this is a human performance. And you can, to solve a task, you need to like visit like many websites, hundreds of web pages, and can easily take 1 hour, and for some cases, like even 2 hours to complete the task by humans. And if you look at the rubric complexity, they are also very complex. It can span like up to like hundreds of evaluation nodes and 6 levels of tree of the depth of the tree. So collectively, just for the benchmark construction part, not including the evaluation part, we spent like at least like over 1,000 human expert hours on constructing this benchmark. And that pays off. Like we did like a human evaluation of the reliability of the judge agents, and we find that actually the judge agents are 99% accurate. So it's very reliable. Right. With this benchmark, we evaluated all the agentic search frontier search systems at the time, and the results are not too surprising. Like, okay, you have these search augmented LLMs. They are not great at these tasks. You have the web agents like operator, also not great, because the operator was not trained to sustain such long horizon tasks. And then for the deep research systems, they are the best. Particularly OpenAI deep research is the very best, but Grok was not too far behind. We also have a human study to just see how humans perform at these tasks. And I think it's very interesting here that humans are actually not great at these tasks. And for reasons like Ross mentioned earlier, that humans are subject to like cognitive fatigue and our limited like working memory, and it's really not great at these like very long horizon tasks. And that's the promise of these agentic search systems, that they can, if we can make them work better, they can greatly complement humans at these complex search tasks. Right, I think I need to speed up a little bit. So that's like evaluation. But you can also see the connection between evaluation and reward modeling here, right? For RL, like for reinforcement learning training of agents, everyone at the frontier labs these days is doing this rubric-based reward modeling. But the rubrics they are using are mostly like simple, like just checklists right now. But you can imagine later we will adapt this like rubric tree-based agent as a judge approach as the reward model for RL training of agents. So next, let's chat a bit about word modeling and model-based planning. This is work led by Yugu, Kai, Yuting, and Boyuan, and in collaboration with Obi AI. Right, so I will go a bit faster here because I think Ross just covered a lot of this context on the planning paradigms for agents. Right, the default paradigm is reactive planning. You just look at what's the current state and greedily decide what to do. It's fast, easy to implement, but it's greedy and short-sighted. And then Ross talks about tree search. It gives you a more systematic search way to search the space. But on the other hand, as Ross mentioned, there are like irreversible actions, and it could be unsafe and slow. So our work actually builds on the tree search work by Ross and Daniel, and their work code base helped us tremendously. So I really appreciate that. But we want to, but just like give you a more concrete example of like these challenges with search in real-world environments. Many of these actions are state-changing and irreversible, so that makes like universal backtracking impossible. And just on a single website like Amazon.com here, you can have many of such actions, like placing an order, making a return, and creating an account, and so on and so forth. And there are obviously like safety risks that other speakers will talk more about, so I'll skip here. So that makes tree search hard in practice. So we want to see whether we can enable a more like speculative planning, a model-based planning, where you have a word model that can simulate the potential outcome of each candidate action, right? Like imagine you have 3 candidate actions, you use the word model to simulate the outcome over next steps, and also like the safety aspects of each action. Then before you have to commit to any of the action, right? You aggregate those like simulations to decide which is the action that's best to take at this point. So it will, if we can make that work, it will be faster, it will be hopefully safer, and it still give us systematic exploration of the space. However, the challenge here is how to get a world model that can work for these computer use agents. Let's start with what is a world model, because this is a heavily loaded term. Here we take a simple definition. A world model is a computational model of environment transition dynamics. So it takes the current environment state and a candidate action and predicts the next environment state. Essentially, if I do this right now, what would happen next? If it's that simple, then why hasn't it been done yet? Well, because it's actually very hard. In the past, in the deep RL literature, right, we do a lot of like model-based planning and world models. But in those settings, we usually have like a simple, single, like simulated setting, like a game. Then we do millions of rollouts to learn a single world model for that environment. Here, for computer user agents, even like if we would just consider the web, even just on a single website like Amazon.com, on each web page, there could be hundreds or thousands of potential actions. And a single website can contain hundreds of different web pages. And now that also compounds quickly if you consider that there are billions of other websites out there. And you want a kind of a universal world model that can work reasonably well across the entire digital world. Fortunately, we find that LLMs, because they are trained on web data and they have a ton of like common sense knowledge, then they are already able to like reasonably predict state transitions on the web. So in this example, if we ask an LLM, say, if I click on this image, what would happen? Then it will tell you that it will probably navigate to a detailed product page, and it will give you this detailed information and maybe another add to cart button. So those information can be very useful for our planning. Therefore, in WebDreamer, we propose this model-based planner for web agents. And it goes like this. So we have a world model, which is simulated using an LLM, like GPT-4o, that's given a candidate state and a candidate action. You can use it to simulate the next state in a textual form. And you can even do multi-step simulation. So you can simulate like what other action you can take in that simulated state and the future state that would lead to. Then we also have a value function similar to the one Ross mentioned earlier that evaluates, okay, at that state, how much progress we would have made towards achieving the goal. Then we can use this for all the candidate actions and choose the one that gives you the highest value, and maybe also hopefully the one that doesn't entail like significant safety risks. Then you can take that action, then the state changes, then you do this all over again. So this is called a model predictive control. Right? In terms of results, on Visual WebArena, and we also have like results on Online Mind Web and another benchmark. I think the results are pretty encouraging. In terms of success rates, the model-based approach is much better than reactive planning, and is approaching tree search approach that requires like a universal backtracking. And then in terms of the efficiency, it's much better than tree search. But I also feel like we are really just like at the very beginning of this. Like for example, we also trained, like we synthesized a lot of web data. We synthesized, I think, like 3 million triplets to train our own world model, 7B model, that can reach on par with like GPT-4o here as the world model. Which is encouraging. But on the other hand, all these models, they fail at multi-step simulation. So it turns out you can do one-step simulation reasonably well, and that's very helpful. But if you try to do multi-step simulation, they all drift away very quickly. So I think there is still a lot to be done for word modeling and model-based planning. And I also know like many of these frontier labs, they are trying to get word modeling for agents essentially into the base agents, not as a separate components. So they merge that into like post-training or mid-training. All right. Finally, I'll talk a little bit about skill weaver. And so we mentioned that we need continual learning. I think at this point, especially for people following who are active on Twitter and saw this like whole debates around Richard Sutton's latest interview with Tâches, like continual learning is not a new thing anymore. But when people think about continual learning, we tend to, as machine learning people, we tend to only think about like parametric learning, right? There is no learning if my parameters don't change. But I think a new kind of continual learning that's emerging with LLMs is what we call non-parametric continual learning. You don't have to change your parameters, which you will suffer from like catastrophic forgetting, ripple effects, and all these annoying issues. You can continue to learn in a non-parametric way. And there are multiple ways of doing that. Here, what we do is we ask the agent to explore an environment, then try out different tasks like Russ did. But instead of like updating the parameters, we build an agent that can summarize or abstract these past experiences into reusable skills, reusable APIs. These are actual like Python APIs, so then you can do all the good things with code like self-debug, like execution tests, and so on and so forth. And then we can also like compose these atomic skills into like more compositional skills and so on and so forth. And then we use this to augment the agents, the action space. So these are more like the high-level actions the agent can take, and that drastically improve the agent's performance. And again, this is still like just the very beginning of this kind of a non-parametric continual learning. Right, so I'll stop here. Just to conclude, I think there are a lot of things we need to tackle to make agents really work at a scale in practice. There are these like core competencies and as well as these cross-cutting issues. In this talk, we touched on several of this, but I think a lot needs to be done. And so my conclusion at the end of 2025 is that we are still at the start of agents. We're definitely not at the end. Yeah, thanks.
Very fascinating work. In the first part of your talk, you mentioned about the parsing, taking the query and producing all these evaluation functions of parts tree, the way you showed. If you go back to the slide, and then the second part is the web generation. If you go to the web generation part.
Web, okay.
Extractor. Is this something that would you do for every new task? Like So I was wondering, like for this task, if given a new task, do you have to go and come up with a new rubric, and who is providing that rubric?
Mm-hmm. So there are a couple of things going on here. For these like extractor verifiers, these are more like intelligence ops that you reuse across rubrics. So you have like a Python function that's essentially an LLM call that can extract certain information from the answer, for example. But on the other hand, for the whole rubric, that's a much more difficult question. There are two stages. First, We develop an code generation agent that will take the task and take the specific other requirements and generates the first draft of these judge agents, including the rubric tree. These rubric trees can easily be like hundreds of lines or thousands of lines. So it's very hard if you ask a human to just write it from scratch. Then the code gen agent will also do self-debug and things like that. Then it hand off to a human expert to just look at it and correct some remaining errors and so on and so forth.